Hi everyone, welcome back to CSCI 100 Lecture 18. This lecture is going to pick up where the last lecture left off, which was in the middle of thinking through how to think about the efficiency of a program, and in particular, time efficiency, how quickly it runs. And we're going to finish off that concept, finish coming up with this idea of big O notation and orders of growth, and see some examples of how it's applied, and also talk a little bit about space complexity. Now, today's lecture is going to be very conceptual, and I'll show lots of examples. It'll also be the mathiest lecture that we have all semester. But it's valuable to understand this concept to know how to think about how efficient your algorithm is, especially when it comes to interviews. You want to be able to say, this is the way I'm solving this problem because it's more efficient than this other way. You have to make your decisions based on some rational thing that you can point to. And that rational thing is time complexity or space complexity. And even though today's lecture will be really focused on ideas, we'll see some applications today, and in class, in the classwork and in the lab, you'll get to practice these time complexity and space complexity ideas more. So we were just in the middle of thinking through how we decide which algorithm is best. And last lecture, we were looking at these potential options for how to walk through a city, tourist walk. And again, we came to this idea of what's best depends on what you care about. And in particular, if we're thinking about runtime, we came down to these three ideas. We could measure with a timer. And in that case, if there's two separate algorithms, we click a timer on and run the program and click the timer off. And we saw how to do that last lecture with the time module. And then we could just compare how long compare one algorithm to another. But the problem that we saw was that, for one, the runtime of an algorithm, if we're just measuring with a timer, depends on the hardware. And so if you use a brand new computer from this year as compared to a computer that's 5 years old, the computer from this year will be much, much faster, much more efficient. We also saw last lecture that it varies from run to run. And so even on your same computer, if you run the same algorithm over and over, each time it runs, it'll take a different amount of time. And sometimes twice as fast or half as fast, like a significant difference, depending on how busy your computer is at the time doing other things. Then we talked about, well, what if we looked at the number of operations? We could say one operation. We could decide arbitrarily kind of what is an operation, and we'll say it takes 1 unit of time, like adding two numbers takes 1 unit, or assigning a variable takes a unit. And then we'll count the number of operations. And we count in terms of n, which was already a big step forward, because then we had a sense of how our runtime changes based on some variable n, which is the size of the input. And so here, this was great. It takes the size of the input as into account. But what is an operation? And we get this big number, like total 1 plus 3x plus 1, which isn't too bad, but with a more complicated algorithm, we can get something much uglier. And that's not ideal either. And so today we're going to talk about orders of growth and big O notation, which is how we finally are going to come to a conclusion on how to abstractly describe the behavior of an algorithm.